In this lesson, we will talk about what is called vector projection. The situation here will be that we have two vectors, A and B, and we want to find what are called the parallel and perpendicular vector components of A. That is, the vector component of A parallel to B and the vector component of A perpendicular to B. We'll call these vectors A parallel and A perp. So what's going on here is that we want A parallel be parallel to B and A perp be perpendicular to B, and we want A parallel plus A perp to be equal to A. Now, since A parallel plus A perp is going to be equal to A, if we can find A parallel, then we need only subtract A parallel from A to get A perp. So our focus here would be to derive a formula for A parallel. Now, a picture might help understand what is going on. So here's the situation. Say here is vector B, here's vector A. Now, in this case, the angle between the two vectors, call it theta, is acute, and the vector component of A parallel to B is this vector. The vector component of A perpendicular to B is this vector. Now, in the case where theta is obtuse, the picture would look something like this. Here are the vectors A and B. There's the angle theta between the two vectors. And then we extend out back this way parallel to B, drop down perpendicular, and this vector here is A parallel. This vector here is A perp. Now, to get started on a formula for A parallel, we need only recall that A parallel can be written as its magnitude times the unit vector that has its direction. So, in other words, A parallel is equal to the magnitude of A parallel times U hat sub A parallel, where we use U hat sub A parallel to denote the unit vector in the direction of A parallel. Now, in the acute case, we see that the unit vector in the direction of A parallel is the same as the unit vector in the direction of B. And in the obtuse case, we see that the unit vector in the direction of A parallel is the unit vector opposite the direction of B. So, in the acute case, we have A parallel is equal to the magnitude of A parallel times the unit vector in the direction of B. And in the obtuse case, we have A parallel is equal to the magnitude of A parallel times the negative of the unit vector in the direction of B. Now, since we already know how to find the unit vector in the direction of B, the only thing missing from our formula is the magnitude of A parallel. Well, using the definition of the cosine function, in the acute case, we see that the magnitude of A parallel is equal to the magnitude of A times the cosine of theta. And in the obtuse case, we see that the magnitude of A parallel is equal to the negative of the magnitude of A times the cosine of theta. So in either case, whether theta is acute or obtuse, we see that our formula becomes A parallel is equal to magnitude of A times cosine of theta times the unit vector in the direction of B. Now, if we had a factor of magnitude of B here, we would have the dot product of A and B, that is A dot B. So to make that happen, we'll multiply by magnitude of B over magnitude of B, which is 1. So we can do that. And now A parallel becomes A dot B over magnitude of B times the unit vector in the direction of B. Now here, of course, we're recalling that A dot B is magnitude of A times magnitude of B times cosine of theta. And we have our formula. Now, maybe a better form for this formula would be A parallel. By better, I mean maybe easier to remember. Would be A parallel is equal to, scratch that, let's say A parallel is equal to A dot unit vector in the direction of B times unit vector in the direction of B, using the fact that the unit vector in the direction of B is B divided by magnitude of B. And this is our final usable formula. Now, note that this is the scalar A dot unit vector in the direction of B multiplied by the vector unit vector in the direction of B. So that means that A dot unit vector in the direction of B is either the magnitude of A parallel or the negative of the magnitude of A parallel. So it's the signed magnitude of A parallel, sometimes called the scalar component of A parallel to B. A parallel itself is the vector component of A parallel to B. Now, to be more precise about which vector is being projected onto which vector, we'll write our formula as projection of vector A onto vector B is equal to vector A dot u hat sub B times u hat sub B. Now, let's do an example. Suppose we have vector V is equal to the vector with components 1, 2, and 3. 1, 2, and 3 are the scalar components. And vector W is equal to the vector with components 3, negative 1, and let's say 4. And suppose we want the projection of W onto V. Okay, here's our notation. Now, we kind of remember the formula. It's the dot product of one of the vectors times a unit vector. And then take the dot product and multiply it by a unit vector. The question is, which unit vector is it? Well, remember we're projecting W onto V, so we want our direction to be parallel to V. That means that the projection of W onto V is a scalar times unit vector in the direction of V. Unit vector in the direction of V gives us the direction parallel to V. So our formula will be W dotted with unit vector in the direction of V, and then we multiply that scalar by u hat sub V. So using the fact that we have the actual vectors W and V, let's see, W has components 3, negative 1, and 4. We need to dot that with a unit vector in the direction of V, which of course is just V divided by its magnitude. Now the magnitude of V is the square root of the sum of the squares of its components, so that would be the square root of 9 plus 4 plus 1, so that's the square root of 14. So the unit vector in the direction of V has components 1 over square root of 14, 2 over square root of 14, and 3 over square root of 14. And then we have to, after we take that dot product, multiply it by that same unit vector. Like so. Now continuing on and doing the actual computations, here we get 3 over square root of 14 minus 2 over square root of 14 plus 12 over square root of 14 is our dot product, and that has to be multiplied by our unit vector, and go ahead and finish the computations here. Let's see, 12 and 3 is 15, minus 2 is 13, so our dot product is actually 13 over the square root of 14. And that gets multiplied by our unit vector. And then go ahead and do the multiplication, scalar times a vector, to get our final answer. It's going to be 13 over 14 is the first component of the vector. 26 over 14 is the second component, and 39 over 14 is the third component. As another example, let's suppose we have a race being run in the direction of the vector, say 5, it has scalar components, 5, 2. So that direction vector would look like this. And then let's say we have a wind blowing in the direction of the vector, let's say 2, 3. And let's say the magnitude of that wind vector is 10 miles per hour. Okay, so here is the wind vector, and here's the direction of the race vector. And let's say we want the speed of the wind in the direction of the race. Well, here we're looking for a scalar. The speed is a scalar, and what we want is the magnitude of the projection of the wind vector onto the direction vector. So what we want to find is the magnitude of the projection of the wind vector onto the direction vector. Okay, so that's going to be the magnitude of, let's see, we're projecting in the direction of the race and the projection of vector D. So the unit vector we use needs to be the unit vector in the direction of D. So our formula for the projection is going to be W dot, that unit vector, U hat sub D, and then times U hat sub D. But the magnitude of a scalar times a vector is the absolute value of the scalar times the magnitude of the vector. And since U hat sub D is a unit vector, the magnitude that we want here is just the absolute value of W dot U hat sub D, which is equal to the absolute value of, see, the components of W are 2 and 3. And dot that with U hat sub D. The components of U hat sub D are, say, D is 5, 2, and we need to divide by the magnitude, which is square root of 29. So the components are 5 over square root of 29, and 2 over the square root of 29. And we go ahead and take the dot product and then find the absolute value. See, we're going to get 10 plus 6, that's 16, over the square root of 29. And of course the units would be miles per hour. That's the end of the lesson.